Good afternoon. Today I'm going through a grade 11 paper, November 2024, term 4, 2024. I'm going through the atmosphere. I'm doing question 1.1 and question 1.2. It's a match question that I'm going to start with. Choose the term in column B that matches the description in column A. Write only letter A to I next to the question numbers 1.1.1 to 1.1.8 in the answer book, for example, 1.1.9J. So let's go through the questions. These are the questions that we have. So you match what is in this column to what is in the other column. So I tried just to fix, because here you can see that there's a number that was missing. So you've got a 1.1.1, 1.1.2, 1.1.3, 1.1.4, 1.1.5, 1.1.6, 1.1.7, up to 1.1.8. Okay, let's go through the question. A contact zone of polar air with tropical warm air. So we are saying now a contact zone of polar air with warm tropical air. I'll give an example so that at least you can have an idea. Okay, when you're looking at this diagram of the global air circulation, remember we have got polar air from the polar high. Okay, we have got polar air from the polar high here. Then we have got the warm tropical air from the subtropical high. So our subpolar, which is at 60 degrees south or north and south, so that's where you've got the polar front. So the correct answer there for 1.1.1, which reads the contact zone of polar air with warm tropical air. So that in that subpolar zone, the warm and the cold air do not mix because they are separated by a front. So the correct answer there is front, which is A. Is front, which is what? Which is A here. All right. Ocean current that originates at the poles. Ocean current that originates at the poles. Let's look at the options that we have. We have got Indian Ocean is not, latitude no, pressure gradient no. It can be the Benguela, which is H. Of course, you can think of the location of your Benguela current where we have got our Atlantic Ocean. Okay, so there is Benguela, which is H. So the correct answer there is what? Is H. Then we move on. Wind that blows from sea to land. Wind that blows from sea to land. What do we call them? We call them onshore. We call them onshore, which is G. We call them onshore. Okay? Remember your air masses, when it blows from the land towards the sea, we call it offshore because it is warm and dry. But this one that blows from the ocean, okay, from the sea towards the land, we call it onshore. We call it onshore. If it's coming from a warm ocean towards the land, obviously it will be warm and moist. If it's coming from the cold ocean like the Atlantic, obviously it will be cold and dry. Or it's blowing from the sea towards the land, we call it onshore. That's the correct answer there, which is G. So we have taken out, okay, onshore there. We've also taken out Benguela there, okay? Then wind that blows parallel to the lines of the isobars. Obviously, we are talking about our geostrophic flow when the pressure gradient is equal to the Coriolis force. That's where we've got the geostrophic flow, okay? So which means our answer there is F, which is geostrophic flow, is F. That is our answer. Our answer there is what? Is F. Our answer is F. Then determines the amount of inflation that the Earth receives. So we are talking about our latitude. Okay, latitude determines the amount of incoming solar radiation that the Earth receives. That is latitude. The closer you are to the equator, the warmer or hot it is. The further away you are from the equator, the colder it is. So that is latitude, which is C. The force that causes air to move from high pressure to low pressure, that is your pressure gradient. Wind, remember, it blows from high to low pressure. That is your pressure gradient, which is D. Okay? Then wind that bring heavy rains to India in summer. Remember your monsoon, reversal wind patterns that result in different weather conditions. Okay? Wind reversal that results in seasonal, wind reversal that results in different weather conditions. That is your monsoon, which is E. Then rotational force that deflects wind, that is your Coriolis force. Remember, In the northern hemisphere, the winds are deflected to the right, and in the southern hemisphere, they are deflected to the left. So it's your Coriolis force, which is F. So that is F. So this is a multiple choice question. I'll just go through it again so that at least you have an idea of what exactly we are doing. Contact zone of polar air with warm tropical air. These two air masses, they are coming from different pressure belts. Like for example, I think I've used this, that you've got your polar here. Then you've got your subtropical high. Okay, so which means we have got the cold from the polar, then you've got the warm from the subtropical high. So they are separated at the subpolar low, where we have got our polar front. That's basically what this is all about. Ocean current that's originated at the poles from the option that we have, that is your Benguela. Then the wind that blows from the sea towards the land, we call it onshore. Onshore. For example, the one that blows maybe from the Indian Ocean towards the land, it's warm and moist because it's a warm ocean. Some can blow even from like the Atlantic Ocean towards the interior. Obviously, it's cold and dry because cold does not hold any moisture. So if it blows from the sea towards the land, it's called onshore. And if it blows from the land towards the sea, it's called offshore. That's what it is all about. Wind that blows flows parallel to the lines of the isobars. This is your geostrophic flow, is the upper air movement when the Coriolis flows and the pressure gradient is in equilibrium. Determines the amount of information that the Earth receives. That will be your latitude. Okay. Then the force that forces air to move from high to low pressure, that is your pressure gradient. Wind that bring heavy rains to India in summer, that is your monsoon. And then the rotational force that deflects wind, that is your Coriolis effect, the Coriolis force, which is F. But let's move on to the next one. Okay, let me go to the next one now. I just want to bring it closer so that at least it's visible. Refer to Fig 1.2 below on tricellular air circulation. Match the descriptions below with one of the polar, Hadley, and Ferrell cells. Choose the answer and write only the cell next to the answer question numbers 1.2.1 to 1.2.7 answer book. For example, 1.2.8 polar, you may choose the same cell more than once. Okay, so this is what we have, guys. I want to simplify this, okay? This is global air circulation in general, but here we are more concerned with the tricellular air circulation, which means we are concerned with our Hadley. We are concerned with our Hadley, Ferrell, and Polar cell. You know what happens, okay? Just to simplify it, okay? Here what we have got the easterlies here, okay? My spelling. Easterlies. We have got the easterlies again here. Then we have got the westerlies here. Westerlies. Then we have got the westerlies again here. Westerlies. Then here we have got the easterlies. Here we also have the easterlies, okay? Here, of course, tropical easterlies, westerlies, polar easterlies, okay? I'll explain later the reason why I'm doing this way, okay? So these are the polar cells that we have. If you can see with this arrow, of course, what happens within the Hadley cell, you can see there's warm air. Warm air by its nature is very light. So what does it do? It rises. So when it rises here, as you can see, when it rises, before it reaches the tropopause, what happens? In the upper atmosphere, in the low atmosphere, it converges. You can see here, there's convergence that is taking place, moving towards each other because it's warm. So it's moving from this subtropical high, or let me just put, this is high pressure, this is low pressure, this is high pressure, this is low pressure, high pressure, low pressure, and high pressure. So it moves from here, blows towards the low pressure. This is warm air that we have here. What does it do? Because it is less dense, it rises, and when it rises, it cools, okay? So it rises, before it reaches the tropopause, what happens? It diverges, okay? When it diverges, when it reaches 30 degrees north and south, when 30 degrees north and south, what does it do? Because now it has lost most of the moisture, it's very cold, it sinks. Then it comes back creating a Hadley cell. Can you see? Then that's how it creates a Hadley cell here, creating a Hadley cell. Same applies with the Ferrell cell. What happens now? It's moving from the subtropical high. It moves towards what? it moves towards the subpolar because this is high pressure and this is low pressure. So when it moves towards the subpolar, what happens? At the subpolar, of course, since it's low, it's forced to rise. As it rises, when it reaches, in the upper atmosphere, it diverges, then it sinks. It comes back again, forming what? The Ferrell cell. Same applies with your polar cell. What happens? This is the polar cell now. It rises at the subpolar low. You can see as it rises, before it reaches the proper purpose, what happens? It diverges. Then when it reaches 90 degrees north, what does it do? It sinks again, forming a polar cell. So this is a polar cell, this is a Ferrell cell, this is a Hadley cell. These are the tricellular air circulation that we have. Let's go to the question now so that we can answer. The first question reads, circulates in between 0 to 30 degrees latitude. 0 to 30 degrees latitude, from here up to there, that is your Hadley cell. That is your Hadley cell. That is your Hadley cell, 0 to 30 degrees. Then the next one, air rises near the equator and diverges polewards. So air is rising near the equator, then it diverges polewards. You can see here, as it rises near the equator, it's diverging polewards. That is your Hadley cell as well. Next one, it reads, the air circulation is in the mid-latitudes. The air circulation is in the mid-latitude. In the mid-latitude, this is the mid-latitude where we have got the westerlies. That is your Ferrell cell. Next one, 1.2.4. Associated with the tropical air mass circulation, 1.2.4. Tropical air mass circulation, which means the tropical air mass is between 0 to 30. That's where the tropical air mass is, which is your Hadley. 1.2.5. 1.2.5, cold easterly winds originate from this cell. 1.2.5, cold easterly. Remember, it's your polar easterlies, which means it's a polar cell. That is a polar cell. Then the last one, the cell generates the easterly wind belt. 1.2.6, easterly wind belt. Easterlies, we have got them in the polar cell. We've also easterlies in the Hadley cell. So it's both polar and the Hadley cell. Then the last one, the trade winds originate in this cell. 1.2.7, the trade winds. The trade winds, we have them in the 0 to 30 degrees north and south of the equator, which is your Hadley cell. So just to write the answer, we are saying now circulates air 0 to 30 degrees. That is your Hadley cell. That is your Hadley cell. Air rises near the equator and diverges polewards. That is your Hadley as well. Hadley cell as well. Air circulates in the mid-latitude, which means this is your Ferrell cell. Air associated with tropical air mass circulation, 1.2.4, that is your Hadley. Then cold easterly winds originate on this cell, 1.2.5, that is your polar. Then the cell generates the easterly wind belt, that is your polar. Remember the polar easterlies and the tropical easterlies, and Hadley cell. Then the trade winds originate in this cell, that is your Hadley. That is your Hadley cell. So these are the answers. I was using this diagram to get all the answers. Remember, the first thing I did was I explained. So we have got the easterlies there in the polar cell. We also have easterlies in the Hadley cell. That's basically what we are saying. The mid-latitudes, obviously, it's where we have got our Ferrell cell. That's basically what I was explaining. So I've done 1.1 and 1.2. I think this takes us to the end of our first lesson on grade 11 revision. Next, I'm going to do the phone winds. I'll do it tomorrow. Thank you so much.